Bonjour.
Hello. Ouais. Hello, Christian. Can you hear
Bonjour.
me?
Yes, perfect. Hi, everybody. Hi, Mathieu. Hi, Mustafa.
Okay. So,
Ok. Et le son, ça marche. Hi, everyone. I'll just test my microphone.
Hi, Graham. Yeah, you well.
Hi, Christian.
Nice to see you again.
Yeah, you as well. Mustafa, how does it sound from our side?
Very good. We can hear you
Great.
well.
Okay, so we have here for the PhD class of Mustafa Shukor. So we have in the jury online, we have Graham Taylor, we have Christian Wolf also online, and here we have Cordelia Schmitz and Vicky Caillou-Shedon, and Mathieu, who's the PhD advisor, and myself, Moana Shepard. So what we said, I just sent you all of you the time for the presentation. So we will start with the reviewers. So Graham, you will start, then Christian, then we will have here, we will go here with Cordelia and then Vicky and Mathieu and myself, we will finish. So we give you 45 minutes for the presentation. And for the questions, if I send you, we discussed of having something around 15 minutes. for the questions for the Q&A session with the reviewers and here. And if per person, yes, of course, per person, and then then this will should be enough. If not, you just let me know. Okay, so the floor is yours.
Thanks, Owen. Hi, everyone. I'm going to present some of the work that I did during my PhD thesis, advised by Shukor, and titled Efficient and Scalable Multimodal Learning. The talk will be decomposed into 4 different parts, ranging from pre-training to downstream applications. Before diving in, I'm going to just give you a high-level overview of what I mean by scaling and efficiency in general. And for this, I'm going to start by the current state of the art. So all of you have interacted with models like ChatGPT, Gemini, and Claude. You usually interact with it through text, but you can give it also some images, PDFs, sometimes video, or sometimes you can speak to it. At the same time, you can ask the model to generate images, videos, and audio. So these models are multimodal models, or specifically are multimodal input, multimodal output models. Before arriving here, we actually just figured out one main thing, which is scalability. So we just find out that if we scale these existing techniques in such a way that we can leverage a lot of compute, we can get to these capabilities. And scalability usually comes with a huge cost, which is reflected by the need of a lot of energy, compute, data, and very complex infrastructures. I want to give you just a few examples of what I mean with scalings. So I'm going to discuss 5 different axes of scalings. The first axis, which is what usually comes to mind, which is scaling the number of parameters of the model, or the size of the model. We went from models of a couple of hundred of million of parameters, like BERT at some point, and now we have models of a couple of hundred of billion of parameters, and sometimes more than 1 trillion of parameters, like GPT-4 or Gemini. The larger the model, the more memory we need during training, and the slow the inference is. The second axis of scaling is actually data. So when we have big models, these models need a lot of data. And at some point, we had very curated data sets, a couple of millions of examples, sometimes a couple of thousands of examples. And now we have data sets at the scale of the internet. So now we talk about web scale data sets. The third axis of scaling is actually compute. So now we have very large models. We have a lot of data. And to train these models optimally, we need to train for very long. So instead of having a single stage of training that can stay for a couple of hours, now we have different stages of training. For example, for pre-training, this stage can last a couple of months. For the mid-training, it can last actually a couple of weeks. And finally, the post-training, which is more about alignment and adaptation to downstream tasks, which can last actually a couple of hours to a couple of days. So these axes of scaling are actually for capabilities. So if we want to have the best model, we need to scale these 3 axes well. The second axis of scaling that I'm going to discuss is about more horizontal scaling, or more about applications. The first one is about scaling modalities. So at some point, we have models that can understand only single modality. So we had language models like BERT that can process only text. We had vision encoders that can do only image classification. And now we move to models that can do 2 modalities at the same time. So usually these models, you give it an image, for example, and you ask it some questions. Or you do the same for videos and others. And more recently, we have models that we call omnimodal. So these models can take multiple modalities as input and also generate multiple modalities as well. So of course, the more modalities that we add, the more complexity that we add to the architecture as well. And finally, the last axis of scaling is actually downstream tasks. So now we have very capable models that can understand many modalities. So obviously, we will try to tackle a lot of downstream tasks. So we went from thinking hard about how to figure out image classification to now focusing more on scientific discovery, multimodal reasoning, and embodied widgets. So the main drawback of all these axes of scaling is actually efficiency. So it's true that we have more capable models that can do a lot of tasks, but at the same time, we need a lot of data, compute, and money. So what I'm going to discuss in this thesis is actually different aspects of efficiency related to these axes of scaling. The first part will be about pre-training. So these are all the techniques that we worked on that are mainly related to architectures and data mixtures. And the second part, I'll move on to post-training and inference, where I will talk more about efficient adaptation and efficient inference. Next, I'm going to discuss understanding to try to understand what's going on inside these models. And finally, about downstream applications, which focus more on robotics applications. So let's dive into the pre-training stage. So this stage is about actually acquiring very high level or very broad models. So these models, once they are trained, they can do a lot of tasks in zero-shot manner. And in this part, I'm going to revisit the main paradigm of doing pre-training of multiple models. And the current way of doing it is by doing late fusion models. So we take existing pre-trained models, unimodal models. We take, for example, pre-trained language models, pre-trained image encoders, and we just stitch them together through a connector, and we continue training on multimodal data. So this covers actually most of the current multimodal models today. And we call it late fusion because the interaction between different modalities happen later than the model. So the vision tokens will start interacting with text tokens only after passing the vision encoder, the connector. Before discussing the main experiments and findings, I want to just draw some distinctions. The first one is about the native versus the non-native case. The non-native is the current paradigm. We start from pre-trained models, and we continue training on multimodal data. The native case is when we start from scratch. So all these parameters are trained at the same time on all modalities together. So there is no precedence for vision or language. It's not like we are taking a language model and adapting it to do multimodal tasks. It's model that trained from the ground up on all modalities together. The second distinction is about the difference between late fusion and this alternative architecture I'm going to focus on, which is the early fusion models. The difference is that instead of having this hard separation between different modules, instead of saying these parameters are actually for vision and these parameters are actually for text and vision, we have simply single transformer that can take all modalities from the first layer. It's called early because the interaction between all modalities will happen in the first layer of the model. The last distinction is about dense versus sparse models. The current way of doing or of training LLMs or multimodal models mainly is about dense architectures. In this architecture, we call it dense because every input token will be seen by all the parameters of the model. While the alternative, which is sparse architectures, or what we call mixture of experts, MOEs, in this architecture, only a fraction of the parameters are activated for each input token. Specifically, what will happen is you will have, instead of single FFN in the transformer block, we'll have multiple FFNs. And we have a router, which is small linear layer that will route each token to different experts. And what we do is basically, we say, for example, for each token, we want to route it to only K out of n experts. So there's two main comparisons that we want to do. The first one is about late fusion versus early fusion. And the second one is about dense versus sparse. So to answer or to address these 2 points, I have these 3 architectures: the late fusion, non-native, or actually the late fusion, the early fusion. Both of them are dense, and the early fusion sparse, or early fusion anodes. And all of these are trained from scratch. So we are in the native regime case. And to do this comparison systematically, instead of just comparing the final performance, we will actually draw the scaling laws for each of these architectures. And we'll compare these laws that I will describe in the next slide. So we'll simply scale the model size, the dataset size, and compute. We will have a lot of points. And then we will compare these points across these 3 architectures. So when we talk about scaling laws, we are actually talking about this main equation, which consists of 3 terms. We have the irreducible term, which is the entropy. We have 2 terms that tell us how the validation loss will actually scale if we scale the model size and or the number of parameters and the dataset size, which is D. So A and alpha will tell us how the loss will decrease, or the rate of the decrease of the loss if we increase the model size, and similarly for D. So what we do with this equation is we will run a lot of trainings. Each one will give us 1 point. And we will use all these points to find 5 different parameters, which are E, A, B, and 1. So we'll fit this law actually for all architectures, and we'll simply compare the parameters, mainly alpha and beta, across different architectures. On the implementation details, we use a very standard setting. We use autoregressive transformer, causal attention for text, bidirectional for images. We use, for early fusion model, we have only 1 linear layer to transform images to actually tokens or patches. For late fusion models, we use typical clip style with an encoder plus an LLM encoder, and we train models from a couple of hundreds of million parameters to 8 billion parameters. We fix the training mixtures. So we train only on 3 domains: image captions, 45%, interleaved documents, 45%, and text only 10%. I'm going to discuss the data mixtures later in this part. But now for all the findings, it's based on this fixed mixture. So the first thing that we find is that native multimodal models will scale similarly to LLMs. So this was a bit surprising to us because LLMs like Chinchilla or GPT-3 were trained on very different setup, on only text. And in our case, we train on multimodal data. It has slightly different transformer architecture. It has different setup. It was done a few years back, later. And what we found is that the scaling coefficients, alpha and beta, which tell us how the models scale or how the loss behave if you scale the model size and the dataset size, actually are very similar to LLMs. And the other finding is that alpha and beta are very close, which means that if we want to optimally scale the model, we need to scale the data and model size equally. We also compared with GPT-3. And GPT-3, it was quite old paper, so they have only one coefficient that we can compare to. And this coefficient is actually coming from this loss, which is just the overall relationship between loss and compute. So compute, which is the flops, and we compute it as 6NV. It's known formula. It's very good approximation of the flops used during training. And we found that actually this loss behave almost exactly as the GPT-3 model. On the right part of this figure, I have just a 3D landscape of the losses. So each point is actually a different training ground. And we have the tokens seen during training on the x-axis, on the y-axis, of the parameters, of the trainable parameters. And on the z-axis, we have the validation loss. So this is what the landscape will look like. Now I'm going to move to the comparison between early and late fusion models. So for these 2 architectures, we do the same study. And here what we plot is actually the relationship between loss and compute. On the y-axis, we have the validation loss. On the x-axis, we have C, which is 6 MB, or the flops. And what we see here is there is no advantage of doing late fusion compared to early fusion. Even if you look at the coefficients, we have almost exactly the same coefficients. So these two architectures will stay similar. The only difference that we found is about the optimal ratio between the model size and over the data set size. So the way to read this figure is to say that given a fixed compute budget, so you have a budget for doing trading, and now you want to decide, should you increase the model size or should you increase the data set size? And what we found is for early fusion models, it's better to keep the model smaller and train for longer. While for late fusion model, it's actually the inverse. Next, I'm going to focus on the comparison between dense and sparse models. So we do the same study, but here, what we actually found is compared to dense models, the early and late seen here, the green line is actually significantly better by doing actually anodes. And on the optimal ratio between the model size and dataset size, we found that actually MOEs or early fusion MOEs needs a lot of data. So these models are data hungry, and to get the optimal performance, you need to train for very long. The last finding is about specifically the mixture of expert architecture. And in this slide, what I'm gonna study is two design choices for the router. So the router, this small layer that actually routes each token to different experts. The typical choice is for this router is to be modality agnostic. So each router will be routed independently of its origin modality to different experts. The second choice is modality aware. And the idea is to, beforehand, saying that we have these experts for image and these experts for text. What we found is on this figure, where we compare the validation loss on the y-axis, and we have the tokens seen during training on the x-axis, what we found is the modality agnostic routing, which is the dense lies here, are always better than the modality aware routing. Which means that if you let the model figure out how to route different multimodal tokens to different experts, it's better to predefine this routing from the set. On the right hand side of the figure, it's visualization of the expert specialization. So experts are different FFNs. And we show these experts on the first layer, last layer, and the middle. And what you can notice is on the first layer, for example, we have image experts, we have text experts. On the last layer, we can't find actually text experts. And in the middle layer, it's actually merged. So we don't have very good specialization in the middle layer. Which is more give us an idea about how the model will actually learn on itself how to specialize to different areas. So as I mentioned before, all these findings are about fixed data mixture. So the scaling loss that we had tell us how the loss will behave if we scale the dataset size, the model size. But it doesn't tell us how the loss behave if we change the quality of the data, for example, or the different sources or the different domains of these data, of these training data. So in this last section of this part, what we will propose is two different scaling laws that take into account the data mixture or the training data mixture. So these models, they are trained on mixture of domains. For example, we had 45% image captions, 45% interleave, 10% text only. So H1 will be 045, 045, and 01. So we'll simply include these mixture in our scaling laws, and we have different forms So we tried different forms of these scaling laws. The most simplistic form, which is just adding an additive term that will depend on HI or the training mixtures. And in this case, we will fit CI. We'll try to find actually CI and gamma I. So we have more parameters to fit, and thus more training has to do. And a joint law, which is more general. And in addition to this additive term, we actually say that A and B will also depend on H. So now, these scaling laws, if they are valid, they can tell us how the laws behave. If I give you the model size, the dataset size, and also the training mixtures. The other finding or the other consequence of these scaling laws is that once we have these laws, we can actually predict the optimal mixture for a given record. So before launching your training, these laws will tell you what is the best mixture for your given compute budget. So I'm going to show you only one figure, which actually highlights this last finding about the optimal training mixture. What you see here is we have the loss, the validation loss. We have the floss on the x-axis. All these points are points used during a training or actually to fit the scaling loss. And on the right side, we have an extrapolation points. So these are bigger models that are never used to fit the scaling loss. All the points in the gray area are many trainings with different data mixtures. And the points in yellow and purple are our training grounds based on the optimal mixtures that we predicted based on the scaling loss. And as you can see here, we achieve actually the lowest loss based on the optimal predicted mixtures. Before finishing this section or this part, I want to just highlight that all the models that I discussed before are multimodal inputs to unimodal output. So all these models will take image, video, text, audio as inputs, and always predict text as output. There's another family of models, which are multimodal input, multimodal outputs. And before without getting into too much details, the main idea behind these architectures are actually tokenization. So the idea is to tokenize all these modalities. Image, video, audio will train different tokenizers. We will get discrete tokens. And then we have unified vocabulary that contains tokens coming from different modalities. And then we'll simply train a sequence-to-sequence transformer model to do a lot of multimodal analysis. So I want to just highlight this architecture that we proposed a few years back, which is called Unival, and can do image, video, audio, text. It's only 250 million parameter models, and it's based on this discretization knowledge. To wrap up, we discussed scaling laws. We showed that actually there's no advantage of doing late fusion compared to early fusion. We showed that MOEs or sparse models are significantly better than dense models. We can actually predict the optimal training measures. For unified multimodal models or omni models, the key behind these models are actually tokenization. And there's one line of work that I didn't discuss, is about the training objectives or leveraging multimodal data when training vision encoders. And in this work, we actually showed that if you take your vision encoder, you train on multimodal data, you get state-of-the-art results. So now I'm going to move on to post-training and inference. In this part, we assume that we have already pre-trained models. So we start from existing pre-trained models, language models, vision encoders, same for audio and video. And we ask a couple of questions to actually, with the objective to train multimodal models. So we have unimodal models, and we need to do multimodal tasks. So should we train from, for example, from scratch? Should we build on top of these existing models? Should we train end-to-end? Should we train only fraction of the parameters, and so on? And the solution that we propose is based on this state fusion architecture, because it's widely used. And what we propose is to simply take all these existing unimodal encoders. They are already pre-trained. Add this connector, this small connector layer, and connect these encoders to a pre-trained language model. So the difference between this part here and the previous part is that here we only train this connector layer. So this connector layer can be as simple as linear layer that connect two big backbones. Specifically, what we propose in EPAM is this architecture that has linear layer as connector. It takes a single vision token, which is a CLS token, special token in the VIP transformers, and inject it into multiple layers inside the LLM. And we train only this connector layer on a couple of data sets, as I will discuss later. We take this architecture and we extend it to a new architecture that we call EPAM. So in this architecture, the main difference is that we invested more in the connector layer. So instead of having one linear layer that connect these two backbones, we have now a transformer module that take all vision tokens and compress them into few learner tokens that are passed to the LLM. And we found also that if we inject these tokens in the first layers, we get the best performance, which is consistent with recent PLMs. On the implementation details, we don't do any pre-training. We simply take this architecture, we train only the connector layer. Sometimes we add some soft prompt, and we train all these data sets. So these data sets are a couple of captioning, visual question answering, audio captioning, video captioning. They are quite small data sets, and we evaluate with standard metrics like accuracy inside it. In terms of backbones, at the time we used OPT and Llama. For the vision, we used Clip, but we mainly focused on unimodal encoders like DIT, for video transformer, and for audio, ES2 memory. I want to show you one result or one main comparison between what we propose in EPAM and DPAM and two families of models. The first family is about large-scale methods. So when I say large-scale method, so these are multimodal models that are trained on massive amount of multimodal data. The first family evaluates in few-shot manner or in context learning, to be specific. The second family contains these models, but also fine-tune. So this gives us an upper limit of the performance that we can have. And the last family of models, which contains EPAM and DPAM, are all the parameter efficient methods. So what we show is actually this EPAM, this architecture that was proposed maybe at the same time as Nando, that we can show that only training actually 4 million parameters, we can get very competitive performance to other parameter efficient methods. And with DPAM, we even push the scores, and now we can compete with large scale methods. Before finishing this part, I'm gonna just mention a few things about efficiency during inference. So EPAM and DPAM are more about efficient fine-tuning or efficient adaptation. But we still have very large models. We have 7 billion parameter LLMs. We have very big vision encoders. And we still have very slow inference. And what we propose in this work is to make these models more efficient. We can actually leverage that redundant computation inside pre-trained LLMs. So I want to highlight that here, the LLM is still frozen. The vision encoder is still frozen. And we are still in the same paradigm of training only the connector. And in this paradigm, what we found is we can simply skip blocks, complete blocks. We can skip FFMs, skip self-attention. We can even parallelize self-attention and FFM, or parallelize two entire blocks. So this gives us a boost in terms of speed during inference with minimal impact on accuracy. So to wrap up, we discussed EPAM and DPAM for parameter efficient fine-tuning to adapt unimodal models to multimodal tasks. We discussed skipping computations to accelerate the inference without losing much in terms of accuracy. And there's another line of work, which is aligned with these two directions, which is about model merging. The idea is to leverage all these pre-trained unimodal models and to merge them in the weight space so we can get better model without doing a lot of them. So now I'm going to move on from training inference to more about understanding and try to look inside these models and try to understand what's going on. The main question here is about the interaction between different modalities. So we take this architecture, the late fusion architecture with frozen LLM, frozen vision encoder, and we look inside the transformer blocks to see how perceptual tokens will interact with text tokens. The first thing that we observed is actually different modalities live in different spaces inside the LLM. As you can see here, so this is a TSME plot of the different tokens coming from different modalities. And we have very good separation between text regions, video regions, image regions, and audio regions. We call these actually different narrow poles because the cosine similarity or the angle between the unimodal tokens are very high. So the similarity between audio tokens are very high. But the similarity between audio and video or audio and image is very small. So that's why we call it different narrow poles. Despite being in different latent spaces inside the LLM, we actually found that these different regions will get closer and closer if we move on inside the architecture. So if we track the similarity between different modalities inside the LLM, we will see that this similarity increases with the length. So we call this the implicit multimodal alignment, and we compute it in a very simple way, which is just only the cosine similarity between the average image token and the average text token. And in addition to this finding, we found also other observations that are very useful for efficiency techniques. For example, we found that vision tokens don't change much compared to text tokens. So thus we can actually skip vision tokens inside these architectures. And each transformer block will contribute very slightly to the residual stream, which motivates actually all the skipping work that I described before. There's a couple of implications for this EMA score, or this multimodal alignment score, specifically for performance in general and safety or hallucination specifically. What we noticed is the higher the score, the similarity between image and text or video and text inside the layers, the higher this similarity, the higher the performance, and the lower the hallucination. In other words, we found that the hallucination is coming partly from the misalignment between different modalities inside the model. To wrap up this part, there is another line of research, which is on the intersection between understanding and efficiency, which is about changing the model behavior without doing any training or any fine-tuning. The idea here is that inside these LLMs, we can associate tokens to different concepts. And because these concepts, or many of these concepts, are actually linearly separable in the LLM, we can find shift vectors. For example, in this case, as I illustrate, it's from yes to no. And we can apply this shift vector during inference to change the model behavior. So what will happen, for example, if I use this shift vector from yes to no, the model will always answer no, whatever the question is. So there's multiple implications for this line of work, especially for safety and debiasing that are discussed more further in the paper. To wrap up, we discussed the implicit multimodal alignment and its implications, performance and safety. We discussed the steering the representation to change the model behavior without doing any training. We have some follow-up works, for example, learning to steer to improve even further the steering by doing some model. And there's other works also about understanding the limitation of multimodal models and specifically target in context learning that we will not have time to discuss today. So finally, I'm going to move on to downstream applications. And in this application, we will take many of the ideas that are presented before and try to implement it in very useful applications, mainly for robotics and high-level planning or design. So in this part, I'm going to focus on this architecture that consists of two main modules. We have the high-level control module and the low-level control module. The high level is more about understanding, planning, reasoning. It doesn't need to be fast. It can be actually slow. And this model will interact with the other module, the low-level control, by sending maybe goals or sub-goals, so that this low-level control can do actually or can execute these actions or these sub-goals in real time. So this module is about very fast execution and going from high-level commands to very low-level actions. Related to this architecture, I'm going to discuss two instances. The first one is VLJEPA for high-level understanding. And the second one is about small VLA, which is more about continuous control. VLJEPA takes high-level goal, can be any textual query, and video as input, and predicts sub-goals, can predict answers, captions, actions. It's very general. Small VLA can take a textual query as well, which can be a very simple task like pick up the cup. It can take also images or video stream, proprioception state, and predict low-level robot actions. So focusing more on VLJEPA here, the architecture has different main aspects that differentiate it to other VLMs. The main one is about the non-generative aspect. So this architecture is trained entirely in the latent space. So there is no token generation. It's not regressive. It's single forward pass. The idea consists of taking a video input, a textual query, and training this predictor to predict semantic embedding in the latent space. We can have optionally a decoder to decode whatever in the latent space. For example, to get caption, get the action in textual form. Specifically, we use for the video encoder VLJEPA2, which we keep frozen. For the Y encoder that take the textual target and embed it in the latent space, we use embedding general, but this can be any other textual encoder actually. And we train this predictor that can be either initialized from scratch or initialized from any good layers. For example, here we take a couple of layers from Llama 3 model. And we train the Y encoder and the predictor with a contrasted loss to avoid the collapse. This architecture is very general that can do many tasks like retrieval, question answering, video captioning, video action recognition, and so on. There's two main experiments I want to highlight related to VLJEPA. The first one is the comparison between VLJEPA or VLM in the latent space and actual VLMs or VLMs in the data space. So we have very controlled setup where we train on the same data, same batch size, same learning rates, same everything. And we compare the performance. So here it's the video caption performance and the zero-shot video classification between these two architectures. And what we found is that VLJEPA learns much faster compared to typical VLMs. It's also more efficient because we don't train the full model. And during inference, because we don't decode every embedding, as I described later, we are actually more efficient during inference. Now, VLJEPA is useful for a broad range of tasks, but one of the main application of this architecture is for video streaming applications. So this application consists of having a stream of videos, and we need to understand the stream of video, for example, do some video captioning, some action detection, event detection, and so on. So because VLJEPA predicts for every chunk of video an embedding, we can actually track these embeddings. And based on the change in these embeddings, we can decide whether to decode, for example, in this case, or not to decode. So the typical VLM will simply take all these video chunks and decode every chunk. While in our case, we can selectively decode each chunk of videos. What we show here is that we can get the same performance by doing 3 times less decoding. I want to finish by a small VLA. I want to go briefly. The idea is actually very similar to the clustering and inference. In this part, we adapted unimodal models, LLMs, and vision encoders to do multimodal tasks. Here we'll do the same and try to adapt multimodal models to do robotics tasks. So VLA, or vision language action models, instead of generating language, as in VLMs, here we generate low-level actions. The main contribution here is about leveraging community datasets. And the second one is about very efficient and compact architecture. So some ideas that we discussed before is, for example, skipping layers. So in this architecture, we skip almost half of the layers. We keep the VLM frozen. We use very small VLM. And to adapt it, we use an action expert. So this can be the equivalent of the connector in the previous part. This action expert is trained to generate the low-level actions and is trained with flow matching loss. We have some efficiency trick, for example, instead of using only self-attention, we interleave cross and self-attention. Now we take this architecture and we want to use it as inference time, but we want real-time execution. And one drawback of the current paradigm of doing VLA inference is actually these idle frames. So what others are doing actually is based on prediction and execution in a sequential manner. So we wait for the model to predict the next chunk of actions. Once it's ready, we start executing it. But if you look at the robot, you will see very clear pauses and idle frames. What we proposed is to replace this with an asynchronous inference approach. And the idea is, it's not completely novel, but the idea is simply to say that you want to interleave prediction and execution. So now the model predicts the first chunk of actions. The robot starts executing these actions. And at the same time, we start predicting the next chunk of actions, and so on. There's 2 tables I want to show. The first one is about the architecture itself. So we take this small VLA architecture, and we trained on a lot of data from this simulation benchmark, Liberate. It's multitask benchmark. And we compare it to other architectures. So at the time, Phi0 was the state of the art. It's much bigger model. OpenVLA was also one of the state of the art models. It was much bigger, 7B parameters. And what we showed that this compact architecture, with all the techniques that we propose, like skipping blocks, interleaving self and cross attention, we can get very competitive performance to these approaches. Now, for evaluation on real-world tasks, I want to highlight 2 main points. The first one is about doing multitask training. So what we show, if you take the same model, you train on the same data, but either you do it single task, so either you train on this task or on this task, and so on. Or you train on all these tasks together, you get more performance if you do multitask training. So we get 11 points more if you do multitask training. The second point is about pre-training. So now if we stick to the multitask training and we simply pre-train the model on a lot of robotics data coming from community datasets, we get a huge boosted performance. So what I want to highlight here is that these VLAs are data hungry and can benefit a lot from multitask and pre-training. To wrap up, we discussed VLJEPA as a high-level model to do understanding. We discussed small VLA as low-level module to do action execution or to go from language to actions. And one thing I didn't mention, which is actually the data set used to train VLJEPA, It's very general data set. It's called Action 110 and can be used for models like GeoGebra, but also PLMs in general or robots in general. I want to finish by a couple of takeaways and perspectives. Maybe one of the main takeaways that we can draw from this talk is first about the architecture. So what I propose is to move toward architectures with minimal inductive biases without any rigid parameterization. These architectures will leverage most computations, and they are more scalable. We showed that actually transformer models, or LLMs specifically, that saw a lot of data can simply generalize to a lot of modalities and can be easily adapted to other modalities. To get more efficient models, we need to find where are the redundant computations. And finally, training in the latent space is actually more efficient, or way more efficient than training in the data space for VLMs. So few line of research I would do if I have enough bandwidth and a lot of compute. First is related to scaling laws, is to move from the general scaling laws for just tracking the performance or the validation laws. And I would like to see some laws that deterministically predict when the model or where the model will start to hallucinate or to start reasoning or to track some emergent capabilities. Related to data mixtures, to move to more scientific approach for the chemistry of multimodal data mixtures. And the idea is to say that before doing end training, if I give you two data sets, you can tell me what kind of capabilities your final model will have. On the post-training and inference, let's move towards more dynamic inference. The idea is to allocate compute based on the query. For example, in case of LLMs, we have very easy tokens, and we have more complex and hard tokens. And the idea is to activate different amount of parameters for different tokens. Also to move to more flexible sparse architectures. So now the mixture of expert architecture is still very rigid. We have different FFNs. Fixed number of FFNs are activated for each token. But we can imagine more flexible architectures where ideally the allocation of tokens will be on the parameter level. The long context inference, the idea is to provide as much as we can in terms of context. And the key behind this is to not treat each token similarly. On the understanding, I think most of the work now is very shallow in terms of understanding pre-trained models, LLMs or multimodal models. We still don't know the actual answers to, for example, if the model are actually doing reasoning, are they hallucinating, when and where, and to push more on the steering actually, and to have more systematic way of taking any pre-trained model, intervening on this model to get new capabilities or new behaviors. Finally, related to applications, I would like to push more on the hierarchical policies that have different systems of control and perception that are running at different frequencies, and to move towards more physical understanding beyond the web or beyond the data on the internet, and towards more models, either in the latent space or in the data space, because each of them has different kinds of applications. I think that's it.
Thank you. Thank you for the presentation. So now we move to the session. So Brad, you have the floor.
Thanks very much. It was a really nice presentation, and I appreciate that you kind of reorganized with respect to the thesis. Like your presentation wasn't just a summary of the thesis, you even dipped into the pre-training and scaling laws first. And yeah, I thought there's a lot of work in this thesis, and you did a nice job to capture the highlights in your presentation. So good job.
Thanks.
So maybe I'll start with a high level question on a theme that you explored quite a bit in the thesis, which was the native versus non-native multimodal or omnimodal models. Actually, maybe I can weave another question because I also wanted to ask you about multimodal versus omnimodal because I remember when 4.0 came out and they were talking about being sort of like omni, but I also don't have a great sense and of sort of like what distinguishes an omni model. Is it like just like modality agnostic or something about like not knowing about the modalities you're going to encounter up front? So maybe you can start by sort of like a discussion of like multimodal and omnimodal because there wasn't a lot of that discussion as far as I can recall in the thesis, and I think it's an interesting topic. And then I'd like you to maybe move on more to like native versus non-native, whether specifically like whether there's a future for non-native models, or do you believe the field is moving towards sort of completely native models?
Yeah, thanks for a question, Graham. So on the distinction between omni and multimodal models, I think this distinction is very loose now. The multimodal models refer to most of the models that we have today, usually multimodal inputs, unimodal outputs, like VLMs, video language models, audio language models. There's a new term which is called omnimodal, specifically refer to models that can do also multimodal outputs. So this is one aspect. The other aspect is to do a lot of modalities. So instead of doing only 2 modalities or 3 modalities, usually do like several modalities, maybe 10, 15 modalities as inputs, and same way as outputs. So some examples of this are maybe Unival that I discussed, but also 4M or some line of approach from ETF that do this kind of models. And usually they have this discretization approach where you simply put all these modalities into shared vocabulary by tokenizing all these modalities, and then simply train on this shared vocabulary. So it's more related to the number of modalities that the model supports, and not specifically to the architecture of the model. Now on the native or non-native, so I think most of the work are doing non-native because it's more practical, it's more convenient. So it's always better to start from good weights and simply fine-tune these weights to your new task or new modality. The non-native or the native or training from scratch doesn't have very broad audience, I would say. It's only for people that have a lot of compute. So if you have a big lab, you have a lot of compute, and you want to decide, should you start training your LLM and vision encoders separately, and at some point mix them, or you should train single model from scratch on all modalities. So I think that targets more this specific use case. I think in the future, maybe big companies will move on to these kind of architectures, because in the native case, you don't have all the biases or most of the biases that you have in the non-native case. So we saw in some of the work that there is a lot of biases coming from simply using a pre-trained language model if you want to do multimodal tasks. And in the case of native, you don't have these biases, or hopefully you have these biases.
Okay, thank you. That's really helpful. Maybe I'll move to a question about slide 26, if you can go back there. So this is a nice this nice result here. You're showing the gray area, this gap between sort of, as I understand it, kind of training the model naively versus doing this optimized mixture in different ways, sort of mixing the data using your approach, and you show a clear gap in validation loss. And when I saw this, my first question was, okay, so how does the validation loss translate to something useful in the real world? And then I noticed in your conclusion, your perspectives, you actually sort of hinted at that, maybe looking at in different angles. But like in terms of maybe you haven't dove deeply into this yet, but how do you see this translating into effects in the real world? This nice effect that you're showing here.
Yeah, that's a good question. So most of the scaling laws work, including owls, track the validation loss, because this is maybe the only metric that we can deterministically predict. Now, the relationship between this validation loss and the overall performance of the model, so there is very high correlation. And we show some of these results in the paper. So we try to fine tune these models on downstream tasks, and we show that we actually get better performance. But the reason we don't have scaling laws, for example, to track the accuracy or CIDR or whatever metric, is because these are not deterministic as the validations. And these are very dependent on the setup, on the fine-tuning setup. If you train the full model, part of the model, for how many steps you train and so on. So I would say there is correlation. It's not perfect, but it's a good proxy, or at least it's very good starting point. If your validation or whatever training recipe you have, if it gives you the lowest validation loss, I think this recipe is very good start point to start exploring for your downstream process.
Okay. Next, I had a couple questions related to the idea about skipping layers or blocks at inference time. And I think you even had a slide to show sort of the various flavors of it that you explored. I remember that in the thesis. So this is an interesting idea, and I just wonder like how you envision this in deployment. Is this something that the model would be trained and distributed, and then different deployers with different kinds of hardware resources would do like performance optimization to figure out the right strategy of skipping and how much skipping to do? Or do you see the need to do further parameter tuning to kind of, if the model is going to be deployed for a long time in this specific skipping configuration, maybe we've determined that this is the right way to do skipping. Should the model be updated to be kind of like skipping aware, or have other parameters adjusted? Because it seems like you are leaving something on the table. If you've done all this training and you have all these parameters, and then like you just skip and set it to skip, and then don't do anything about it. It seems like there could be additional benefit to making the model kind of aware of the skipping.
Yes, so there's two points related to this question. The first one is that I don't think we propose a very general recipe, or in other words, we don't, for example, propose that if you skip every 2 layers, you get the best optimal performance of your model. What we propose, or actually what we study, is something very specific or very dependent on the downstream tasks. So some tasks, for example, benefits more from skipping blocks. Some tasks are harder. And in this case, maybe you can only skip the FFN, not the entire block. Maybe for other tasks that are very easy, you can maybe skip half of the blocks and so on. So it depends on the complexity of your downstream tasks. The other aspect, or the other point, is that this part is more related to the understanding part than the efficient inference part, because it was mainly to study the redundancy in these pre-trained LLMs. So I didn't have in mind to have very general recipe so that everyone can simply use it, but more to show that actually you don't need these big LLMs for every multimodal task that we want. So you can skip a lot of parameters and keep very good performance. So I think this chapter is more from an understanding perspective rather than like very practical perspective.
Okay, I see. So you're actually from a practical point of view, you're not advocating they be deployed in a skipping sense, especially if the model is going to be used for different kinds of tasks. But you're using this as a way of advocating for more efficient models, even if you aren't skipping at inference, but you're just saying that there's a certain amount of optimization you could do with respect to model size, and the skipping kind of exposes that.
Yeah, exactly. I want to just add maybe one minor point, that in this work, what we showed actually, if you take any pre-trained model, you skip these layers, you reduce slightly the accuracy. But if you want to bridge these accuracy, you can actually train this model. And when I say train this model, I mean only that connector. So you keep the element frozen, you train only that connector, and you can get actually much higher performance. So of course, if you train the full model with the skipping, you get even better performance. But this was not the main point of these kind of works, having like very
Okay.
different.
And then what you're saying about sort of, or what you said about the task specificity before, sort of like the actual, like the type of skipping or the skipping recipe was very task specific. Like to do this additional training might be um, more successful in situations where a model might be deployed on a single task. Like it's doing inference with respect to something very specific, and it could be optimized in that sense. But that may give, if a model is sort of a more general model that many people are using or people are doing general queries, that might not play out as well.
Yeah, that's to some extent what we wanted to say as well. I think it's still not for a very specific task. Like, for example, it's not per data set, but a lot of applications, for example, in the case of VLAs or like vision language action models, we start from very general VLMs, but usually we don't need a lot of these parameters. So the VLMs have very broad knowledge that we don't necessarily need for doing low-level control. So in this case, we can simply skip blocks, as we show in the small VLA paper, and still have very general model, but in the setup of VLA. So it's not per data set or like very narrow or very specific, but yeah, it depends on your setup and the complexity of your task.
Okay. Okay, thank you. I'm just checking my time. Okay, I have a few minutes left, so maybe I'll ask one more. Yeah, so I think I really enjoyed reading the final section of the thesis, which was about VLJEPA and small VLA. And you built a very nice story, particularly in the introduction section around those works, where you talked about these action VLA models being could be basically high frequency models, and you talked about so them being deployed asynchronously as well. And then you had this maybe a VLJEPA model that, as you described in your presentation, maybe being sort of on the order of a few hertz, making higher level decisions. And you talked about them sort of like being in this paired setting and using them together. But then when we get into the chapter, it's kind of like, okay, these are two separate papers, looking at these models, kind of independently, and they aren't brought back together. So I think that I was just, this is not so much a criticism, but I'm curious whether this is going on in the background, like whether these two models are indeed being brought together, maybe at a company, or this is work in progress, or sort of like what is going on in the direction of like pulling these two pieces together in the way that you described in the introduction of that chapter?
That's a very good question and very good criticism, I guess. So yeah, it's two different papers, two different setups. When we did these papers, we didn't have in mind this high-level, low-level architecture. I just like stitched them together in one chapter and draw this story. On your second point, yeah, I think there's a lot of ongoing work on these multi-systems for robotics specifically. I think there's many companies that are doing this. Maybe I can't speak to other companies, not specifically to what I'm doing, but other companies are doing now different systems, system 0, 1, 2, sometimes 3. And the idea is to have very high level model that can do the planning, long horizon planning. You have different low level models that can take this plan and decompose into subplans, and from subplans to low level actions. So there's a huge interest in these architectures, and there is a lot of work ongoing. But yeah, we didn't do any of this during the thesis.
Okay. Yeah, I think I'm pretty much at a time or 1 minute under or something like that. So I'll pass it on to the next examiner.
Yeah, thanks, Shukor.
Thank you. Yes, please.
Thank you. Thank you very much for the presentation. Very nice. I'm impressed by the number, as Graham also said, the number of contributions had in your document, and I counted the number of papers. unheard of to see so many published papers in a PhD. So my first question is a very hard one. How much compute did you use?
It's hard to track, but relatively to what others are doing, I think it's relatively small. So I wouldn't say I crossed the 10 billions in terms of compute used during the thesis in general.
So how many clusters did you combine? Where did you train that?
So it depends on the projects. Some projects were a collaboration with Apple, so we used the Apple cluster. Some with Meta cluster. Some with HF cluster. Some on Hugging Face. Some in the university. So it's a mixture of clusters, I would say.
Okay. Thank you. I will not be able to answer questions on all the chapters, and I might jump a little bit around because I will order it more from about priority and interest. I'll start with the beginning, actually, chapter 3, um, on uh, on training frozen LLMs and frozen encoders. And so my question is, how surprising is the fact that linear projectors actually work, given that linearity is an extremely strong constraint, right? So you take linear functions and you have completely different embedding spaces. What conclusions do you draw from the fact that linearity works?
So I think the main point is to say that once you have very good unimodal models, you have very good vision, audio, or text encoder, and you want to now bridge these modalities, this bridge is actually very easy to get. So linear layer or like small MLP or small nonlinear layer, it doesn't matter. What I want to say that with very small amount of parameters, with very simplistic architecture, you can simply bridge these different modalities together.
Okay. So if I'm a scientist, and when I see that something simple works, which I would have suspected, and I certainly would have suspected to not work, right? So if I think something complex should work and something simple works very well, I'm surprised. And then I say, okay, how far can I go until it breaks? So I don't know if this is a stupid question or not, but can you go further? What is even simpler than linear? Even simpler than linear would be linear low rank, right? Could we do low rank adapters? And how low rank can it be? What happens there, right? What do you think?
Yeah, that's a good point. So I think you can go like with LoRa or any low rank linear layer. I think this was the simplest way to do it because we had different dimensions for the vision encoder and the LLM, so we needed to map these dimensions anyway. So that's why we used the linear layer. We didn't try with something smaller or with lower rank, but it should work. So in some follow-up works, what we showed that if you actually add more parameters and you complexify slightly this connector, you get better performance. So the linear layer is more about understanding these models. But if your goal is to get the best performing model, I don't think you should use linear layer.
Yes.
And you need to throw as much compute and as much trainable parameters as you can.
Okay. Thanks. I would like to make a connection to the understanding chapter. So at some point you show that these embeddings live in different spaces, in different cones, but then if you go up the layers, they become similar, etc., etc., etc. And I found the chapter interesting, but I was missing a high-level take-home message. So what is actually happening there? You project visual tokens and text tokens together. You check how close they are, but my question is, and you allude to that in your text, in your introduction. Is it actually that the language model is used as a universal computation engine, which actually abuses its own pre-training to reason actually in vision space, right? So there is no language ongoing, or are the vision tokens projected into language space and then trained by dealt by a proper language model? These are two extreme cases. Do we know what happens in there? Do you have any conclusions? Anything to share?
Yes. So we detail a lot of these discussion in the paper, but to summarize, let me start by the first or motivation why we did this study. So the first motivation was, or our most earliest explanation why these efficient techniques work, or why we can adapt frozen LLMs to multimodal tasks, is because this connector will simply map different modalities to the language space. And now, like, the vision token will be transformed somehow to a textual token, and then the frozen LLM will simply see only text tokens, and that's it. So this was the story or the motivation why we did this. And it turns out that this is not true, or maybe entirely false. And looking inside this model, we actually noticed this like very different regions that they are aligning across blocks. And I think the main takeaway is, I don't think it's about pre-training on language or pre-training with next token prediction. It's more about this general architecture, this general transformer architecture with residual streams, with successive blocks. These blocks are very similar, or exactly the same terms of architecture. And based on our analysis, what we found is each of these blocks will contribute slightly to the residual stream, and which makes it very general to actually handle very heterogeneous tasks. So I don't think we went very deep in this architecture, or we have like full explanation why this transformer is very general. But I think this was the main takeaway, that these LLMs generalize to multimodal data because this architecture is very general and can handle this heterogeneous data.
So it could be that the LLM is basically just used as some universal computation engine, right? Which is running out of distribution with respect to actual language understanding. This could be hypothesis, right?
Yes, true. I wouldn't say LLM. I would say a transformer model pre-trained on a huge amount of data. With LLM, I think if we
Yes.
same on image data, I wouldn't surprise to have the same findings for text, for example.
Okay. Thank you. I'd like to make the jump back to the chapter 3 on the simple versions where you have like linear projectors between frozen models. My question is, there are a couple of the benchmarks on which you train them. So most importantly, VQA are known to have strong biases. So can you completely exclude that the frozen injector basically overfits on the biases? So that basically you get all these results because you exploit correlations and not real reasoning.
That's totally possible. So maybe a few comments here. First, in terms of the benchmarks. So VQA is about, so there was a first version of VQA, which has a lot of biases, textual biases. I think most of these biases are fixed in the VQA v2, but still we have some biases. I don't think we look too much into the biases in these models. It could be that the models are exploiting these biases, but given that we have very competitive scores to other models, so I would say the same for other models as well. So it's possible, but yeah, it's a possibility that there is biases that these LLMs are exploiting, and they are not truly doing multimodal understanding or anything.
Okay. Yeah. I was not targeting in particular yours, by the way. This was more questions on generally these type of models which do these projectors. Okay. Thank you. I would like to come back to one of Graham's questions. He asked whether native training is the future, and your answer was that you remove biases which you have in the pre-trained model by directly training it on non-multimodal data. So there is an obvious follow-up questions. What other biases do you get by native training because you train them on multimodal data, and these mixtures are not, there's no natural mixture, right? I mean, there are other biases in these models. So do you suspect that you get some of these biases or not? Or what are they? How different are they?
We might get some biases, but I have no idea what kind of biases we might get, because the biases that we study and I have mine are mainly due to having something in the first place and trying to adapt it to another setup. And all these biases are coming from this thing that was in the first place. So in case of the native, because there's no precedence to anything, I'm not sure what kind of biases we can get. But the question is, are we going to get the same performance, the same capabilities or not? I think this is still an open question, but I believe it to be true.
Okay, thank you. I could have tons of questions on here, but I would like to talk about robotics. So let's jump to the last chapter, and I actually would like to start with real chapter, and I alluded to this in my report. Honestly, I didn't understand a couple of the things you explained. I know what autoregressive means. I know how LLMs work. I know what teacher forcing is. So there is no issue there, I hope at least. I know how video chapter works, how video chapter AC works. I did not understand what you mean by autoregressive versus single forward pass, right? Because single forward pass, everything is pretty much a single forward pass. So I don't see how autoregressive can be the inverse of the single forward pass. So basically, when you do streaming, and you alluded to streaming, right? You apply your models to streaming, that means that you need to take a decision at each time step, right? At each time step in your decision. And normally you need to take the decision on the full observation history. So either you have a full attention-based model, which means you attend over the full history and you're O of n, or you have a recursive model and you can be O of 1. And both of these, for me, they have different complexities, but they're independent of whether your model is autoregressive or not. So for me, autoregressive is not the bottleneck. It's the architecture which determines your complexity and not the fact whether it's autoregressive. Or did I misunderstand something here?
Yeah, when we say autoregressive, it's mainly about how the model will generate the output or how the model will generate the answer. So for LLMs, they will generate the answer token by token. So if you are doing video captioning, you will generate your answer token by token for the given video chunk. Now, in case of ViaJava, you take this same video chunk, you do one inference, you get an embedding for this caption, and then you can find the caption by doing the closest, by computing the distance and getting this caption. So you don't need this autoregressive generation to get your answer.
Okay, that's what sorry. No, go ahead, sorry.
Yeah, so related to, in the case of video streams, I don't think we are doing anything fancy here. So what we do for video streams, we take each chunk independently. There is no history. And we encode these chunks independently. So I think it's orthogonal to the architecture that we are using.
Okay, so yeah, this was a little bit mixed up in the document, and I think indeed. So I understood the first part, but then in the context of streaming, it doesn't really hold, right? Because of course, if you read a single video as a chunk, you encode it, and then you're still autoregressive with respect to the text, but not anymore with respect to the video. But that doesn't hold anymore if you do video streams, right? Because then you need to have a sliding window over your video stream. So, okay, you can chunk it. There are indeed a couple of papers doing it. The Markovian thinker, for example, does this as well. But you don't fundamentally change the game, right? So you chunk it together, but you still have a history and you still need to read a stream. It's just that you downsample temporarily, right? You don't change the game. So I think this was perhaps a little bit, at least for me, confusing. I think the document might need a couple of more explanations on that.
Yeah.
Yes.
I think autoregressive, non-autoregressive, it's I wouldn't say this is the main point behind the algebra, or I don't think this is like the main drawback of current VLMs that we want to get rid of. It's just like an aspect of this architecture that at inference time, if you want to generate your answer, you can get it faster if you do one inference with the algebra compared to doing token by token prediction with VLM. But for video streaming, the same will hold for both architectures.
Yes, it's independent. It's
yeah.
independent of the chip architecture. That's exactly my point, actually.
Exactly.
Yeah. Okay.
I agree.
I have a last question on small VLA. I have lots of questions, but let's ask a single one. There is lots of talk on VLAs, and not just, I'm not singling out smaller way, but VLAs in general, also Pi Zero, Octo, OpenVLA, all these families of models, that they are terrible in OOD generalization. So when you look at, even in most manipulation benchmarks, the notion of task for somebody like me who's coming from other robotics tasks like navigation, the notion of calling the same thing a different task if just the object moves 30 centimeters is a little bit strange. But this is how it works in manipulation, right? You change the color of the object, you move it half a meter, and it's become now a different task. It generalized to these different tasks. But there is lots of talk that these models do not generalize well to out of distribution configurations, so they overfit to the initial conditions. Can you confirm that?
Sure. Yeah. I think no one of these models, not only VLAs, but I would say the majority of all robotics policies don't generalize well. So I think it's true. And I don't think there is a reason for them to generalize as well. So the way
So what's the way out?
with imitation learning to fit these low-level actions, these low-level non-semantic actions. I don't think with this way of doing it, we will get generalization. But yeah, it's true for small VLA, it's true for all other VLAs as well. And the way we handle it now, at least in industry, is we add more data, we add more context, more scenarios, more setups, more randomization, and that's it. But we didn't solve yet, or I don't think we have an idea of solved yet the generalization for it.
Okay, for me, this kind of it's surprising because it would, for me, I would have hoped that the power of the VLM, which is part of the VLA, would have solved this generalization automatically, right? It should have understood that, okay, there is a red cube here. I replace the red cube by the yellow cube. The VLM knows the difference, does all the grounding, and the action expert generalizes, but it does not. It's unfortunate. But this is not a criticism of smaller relay. It's great work. We actually use it as well. So
yeah,
thanks for that.
Maybe you want to comment?
Just one point, if it could be a choice as well, because we have afternoon. So
Okay.
you can go there and this would be the last.
Okay. I just want to mention briefly, there's some work that pushing for more generalization to VLAs, especially by doing joint multimodal training and VLA training. But still, it's not very good at generalization, but it's way better than previous models.
Yeah.
Thank you for all the questions. Congrats for your work, and sorry, Mr. President.
No, it's fine. No, it's fine. You just I have to be sure that they do one last time. So thanks for both of you. So now we keep the floor to Tanya. You want the map? Maybe
Yes, I want First of all, thank you for this very nice presentation. We did a lot of different things with your PhD. So maybe we can just start where the other person ended. So actually I have, like, just following up on this question. So how would you, if you go to the comparison with the state of the art, maybe you can go to this data on slide 50, I think, yeah. So how would you explain, I mean, what is this data? There's a Libre data set, right? And so what did you do for training? Did you just train on this data set, or did you pre-train on other data sets?
So Libero is this simulation benchmarks that contain maybe 40 different tasks. We have data set coming from this benchmark. I think this data set was released by Physical Intelligence, the company behind Pi Zero. So we take the same data set, we fine-tune the model of this data set, and then we evaluate on these different tasks without specific fine-tuning.
Yeah, but you pre-train on the test training set of Libre, right?
Exactly. Yeah.
And the model before was pre-trained or not?
No. So these small VLA models doesn't have the pre-train of small VLA. So this comparison is mainly about the architecture. We take this architecture from scratch. We train on this Libero dataset, and this is how we evaluate it. Now the other models are, of course, pre-trained. So we just simply fine-tuned these models on this dataset.
Right, and do you have any intuition that if you would fine-tune your model, pre-train your model before, how this would change the performance of the generalization?
It depends how close the pre-training data is. But I would say if we pre-train it on similar data, especially like for single arm, so this liver was single arm data set with maybe same degree of freedom, I think we get better performance. But further the pre-training data to this simulation benchmark, the further this data is, the lower the transfer is.
Yeah, okay, so basically what you're doing is you're kind of overfitting on this data set, and that's why a small model is good enough, right? That's kind of the explanation.
Probably.
Yeah, because I was wondering why it was good enough, but it's explanation that it's a very small data set, very constrained, right? I mean, basically it's the training and the test set, they're very similar.
Yeah, but the thing is we did the same for other models. So also for Pi0, it's pre-trained, but we fine-tuned on this specific data set.
Yeah, no, I get this, but basically given that those models have a larger
Oh, yeah.
capacity,
Yeah.
they could do other things, right?
Yeah.
And so here you're just having a very narrow space for evaluation. And so this brings me to my second question. How would you say this model is different from the other state-of-the-art models? Maybe you can say a bit by going into the model and
So
it's different.
the architecture follows closely the Pi0 architecture. We start from DLM, we add an action expert, it's trained with slow matching. It takes 3 cameras as input, text, proprioception. I think the main changes are the data first, second, the architecture. So we focus more on efficiency. So we skip some blocks, we introduce set plus attention in the layer. We reduce the number of vision tokens to process the cameras. So this is one aspect. And the other aspect is that these community datasets are simply all the datasets uploaded to the Hugging Face hub. So these are usually small datasets for people collecting data at homes. So I would say these are the two main differences to other big VMs.
Yeah, right. And how do you have any intuition how the data impacts the performance? What is this community data set? It's not just people, right? It's other data.
So this, so it's data sets of the robots that we had at HF at Hugging Face. Usually are for single arm robots, and we collect like hundreds of pieces of data and simply pre-train the model on it.
Okay. What are you reporting here? Real world, you said.
So we have 3 tasks: pick and place, all 4 cubes, pick and place, stacking, putting cubes on top of each other, and sorting. We have different bins, and we want to sort cubes based on colors. And for each of these tasks, we have 50 demonstrations. So we collect 50 demonstrations, and we fine-tune the model at these demonstrations.
Then what's the training, the testing, 50 times?
I think we test, so for each point, we did 10 trials, and we report the average success rate.
Okay, and so here basically you show that pre-training by success, and you don't fine-tune it on real world data. There's we had 50 data.
So here we always fine-tune.
Okay, you always fine-tune it, so here
Yes.
you can see that basically pre-training helps.
Exactly.
As well as if we.
Yeah.
Okay. And then, one more question here, actually, how do you explain that this multitask helps so much? Do you have any explanation for this?
I
It's
think,
like 11% improvement by doing multitask training.
yeah. So one thing about these tasks is that they are very similar. So all of them about manipulating cube, but each have different tasks, like big place, stacking, sorting. But for example, all these tasks contain the same action of picking the cube and putting it somewhere. So I would say this benefits from multitask is coming from that these tasks are actually very correlated, and there is some synergy between these tasks.
Okay, the model is also not pre-trained, right?
So in this case, yes, it's not pre-trained, but it's fine-tuned on all these tasks are the same.
Yeah, but that's why you get so much gain from the multitask, because it wasn't pre-trained before,
I see.
right? So that's why if you just have one task, certainly one task performs better than multitask, right? I mean, especially if you fine-tune it. But if you have not enough data, if they're very similar, I guess it gives a big boost in performance.
I would say yes, if you have very different tasks, it's the case. But I think if you have very similar tasks, maybe fine tuning on all these tasks is better than the single task.
Yeah, but usually you don't get 11%.
Maybe it's, yeah.
I find it surprising. Anyway, thank you. The library having the low library is very useful. It's very good. So, and then what else? So this, yeah, I have one more question for this robot models. This VLJEPA, if you compare it to standard VLA, it was slides before. Can you explain why actually you get this big gain? I mean, because again, I feel like usually I don't observe such a big gain. Does it come from the pre-training or the better features, or what's the gain coming from here?
Yeah. So I think it's coming mainly from the how we train via Java, or specifically that we train in the latent space. So in case of VLMs, let's say in case of VLJEPA, the target is actually much simpler than in case of VLM. So for example, if you're doing question answering or captioning for VLM, you are actually training the model to not generate the semantic answer, but all the superficial features with it, like the exact wording and so on. While if you move to the latent space, you compress all these features to semantic embedding, and thus the training will be much simpler compared to token space. Yeah. So I think this is the main.
Okay, this is interesting. So basically you're saying the fact that you compress in latent space, it's similar to what you do in diffusion generation models, right? You also compress in latent space. This brings you a huge gain because you don't have to look at all the pixels and learn from all the pixels.
Exactly.
Okay. Okay. Yeah, thank you. And then with respect to the data mixtures, so you said like you looked at the data, but I guess it's very important of what kind of mixtures you use. Do you have any insights of how data sources? I mean, basically you show that data helps, okay, this we know, but then probably the quality or the sources of the data are even more important, right? Especially if you have large quantities. Did you explore this or you haven't had this in detail?
Yeah, we explored this extensively in that paper. So the reason I didn't mention the exact ratio or the optimal ratio because it's setup dependent. So for example, we found that the ratio of captioning compared to interleaved depends on the downstream tasks, but also depends on the architecture. For example, there's some architectures, which is the early diffusion models, favor more the interleaved data compared to the captioning data. For LLMs, it's also dependent. If you have, for example, if you want your model to be very good at coding, it's better to have more data coming from coding, Stack Overflow compared to text, Wikipedia, for example. So it's very set up and downstream task dependent.
Okay, and so what would you recommend if you were from, I mean,
Yeah.
all you're giving is like recommendations, so if you have like whatever one task, then how would you go ahead and read all the papers and see what's specific for different configuration or?
Yeah, so I wouldn't recommend taking any number, any absolute number from the paper and use it as is. But I think the main idea behind this is we showed that you can fit the scaling nodes with very small scale experiments. So if you want to train your 3B or 7B models, you can train your couple of hundred of million parameter model, fit your scaling nodes, and use these scaling nodes to predict the optimization for large models.
One more question, you showed this different modalities live in very different spaces, maybe you can show.
Yeah.
Yeah, this is something which I also observed. Do you have an intuition why this happens and what you could do? Because it's probably not a good thing, right? Because somehow it makes things not comparable.
Okay, so we observed, for example, that the norms for the vision tokens are much higher than the text tokens.
What?
The norm, if you track the L2 norm of the image tokens, they are much higher than, for example, the text tokens. But I think this TSNE plot will do the normalization, so this is excluded. If your question is related to how we can merge these regions further, I think it's going to come from longer pre-training, more data, more parameters, maybe unfreezing the model.
But where does it come from? Actually, you know, I mean, apart from minimization, there must be some other.
So the data is very different, right? It's heterogeneous, so we expect to be different. So I think each modality has different aspects, different features. So that's why they are mapped to different regions inside the model.
Okay, but then as you said, in the end, you would want them in the same space, right? Because you want to keep
Oh,
them.
that's we don't know actually. So we want them to be closer, but I'm not sure we want them to be exactly alone.
You think it wouldn't be useful to have them?
I think if you align them exactly the same point, we'll lose a lot of the multimodal features.
Yes, you say you would lose modality specific information.
Yeah. So these models are supposed to be complementary. So if we force our training objective to map them to our one point, I think we'll lose this complementary.
Okay, but you say they would go back closer if you have longer retraining, or
Yeah.
I guess different classes also, right? Depending on your class. Okay, maybe two more questions about how much.
You have to answer the examples. If you need 3, 4.
Okay, two more questions. First of all, what do you see? You said like in the future work about role models. So what do you see there as the most promising research directions?
So I know there's people very opinionated about latent space world models, some other on the data space world models. I think both of them are very important. So for the latent space, I see it more on the planning side. So we train latent world models in latent space, and then we can use them for planning for robotic policies.
Mhm.
All the world models in the image space and the data space will be actually mainly used for evaluation and for data generation. So we can generate a lot of data using these actually video models and the video models. So I see both of them in the future, and each of them has different use cases.
What is for you the difference in data space and data space? Data space would be just generating pixel sequences.
Generating videos from different actions. This is data space. Latent space generating embeddings from different actions.
Okay, but you could have some versions which combine them somehow. Right?
You can imagine such actually.
Okay, but so you don't have any more clear insights on you would use them for robotics, for example, or something else.
So they are still useful for robotics. The latent space, one good thing about them that they learn faster, and they are much more efficient during inference because you are predicting the latent space. They are useful for planning because you don't have all the features that you don't need. You just have the features that are semantic and needed for planning. For data space, you care about the aesthetics. You care about to have very realistic images, very realistic videos. So I see both of them useful for robotics as well.
Okay. Yeah, but I guess you can also use them for low-level control, right? I mean, there's some papers which do this.
Yeah, there's some work that also use data space and latent space for low-level control. It depends on how you condition your model. Is it low-level actions or high-level actions?
Yeah, okay. And then maybe one last question. So now this small VLA, what do you see as next steps? Are you continuing to work on this or?
Not small VLA specifically, but yeah, the next steps would be to integrate this model into the full architecture of model system architectures, where you have high-level, low-level processing.
System 1, 2 approaches.
At least 20.
Okay, thank you. Oh, what would be more than 2?
Yeah.
But would be 3 and 4? What do you see?
So there's other works doing 3 and 4.
So what would be
So the system 2 will be similar to small VLA. System 2 more for reasoning, system 2 for like getting these subtasks to actions. System 0 is more for very high frequency control. If you are controlling a humanoids and you want them to be very stable, so you need a policy that runs at 300, 500 hertz. So this is the system 0. It's usually trained in RL and simulation. And system 3 is for very high level planning. If your task is, for example, clean the house, you want your high level model to predict very detailed plan.
This would be the system 3 would be the planner, and then what system 2?
So usually system 2, it depends. Some people mix 2 and 3, but usually it depends on how long you want to plan. So system 2 is for short-term planning, maybe tasks that can run for a couple of minutes, 10 minutes, 15 minutes. System 3 is maybe for a couple of days, couple of weeks.
This is just the granularity of the hierarchy. It's 3 levels of hierarchy instead of just having one. Okay, thank you very much.
You can take it. So now you have a vote.
Thank you. Congratulations, it's very nice work. Thank you for the clear and online presentation. Congratulations to solve the material for supervising this thesis. So I will start some questions. Sorry, I will start with the data. Maybe slide 20. Would be good. So for this, I was wondering if maybe 2 things here. You said that models go from 0.3 billion to 8 billion parameters. So I was wondering here, what type of tasks did you do exactly, and what type of data do you have for this? Because 8 billion parameters can be quite a lot, or quite not even at all, depending on the task.
So in this stage where we do pre-training, we train actually on these mix of data sets. So specifically, image captions are all paired image text data. So we have an image and a small description of this image. Interleaved is more general. We have interleaved documents, arbitrary number of images and text inside one example. And we simply pre-train with next total prediction on all these data. And that's it. We don't do any fine-tuning for specific tasks.
Okay, and I was wondering for this, again, like 2 slides maybe later. So here on the left, on the right-hand side, you said that basically it's data. Can you recite how we should read the one on the right?
Yeah. So we start from fixed compute budget, C. And over D is actually the optimal model size over the optimal data set. So because you fix your compute budget, now it's tight. You cannot simply scale both of them. You need to decide which one you scale better. And we simply plot this ratio. And as you can see here for the early fusion, because the plot is lower, which means that it's better to increase the D over the N, and for later zeros.
Okay, and in this case, what if you were to have a small model, but train on more diverse data? Because the data, I guess, you increase, but from the same domain. But then, if you were doing different types of training or different pre-training strategies or mid-training or anything else that you mentioned in your introduction, how would this affect the results?
Yeah, so that's a very good question. I don't think we explored this question for different architectures. So all the study that we did for the different data mixtures, which allows us to draw some plots like this, we do it only for the early fusion case. So we don't have these plots with different data mixtures as well. I don't expect to change much, but I expect it to change like.
Okay, and this, again, what about the modalities?
Yeah.
How are modalities distributed in this data? In one modality.
So in this case, what we tried with this ratio of 45%, 45%, 10 is to have almost equal number of image tokens and text tokens. So this is why we actually chose this one. But again, I expect slight changes if we change the data mixtures. One thing we actually studied is if we increase the amount of interleaved data. So if we increase the amount of interleaved data, we'll increase the amount of text tokens because we have more text tokens in the interleaved tokens. We get more benefits of early fusion models. So this is the only one point that we study in this chapter.
And in this case, do you expect, like, do you think that if you had infinite time, what ratio would you choose between modalities?
So if you want a model that is equally good in all modalities, I don't think you need to have equal number of data coming from these different modalities. I think we studied this extensively in the data mixtures. I think we have some messages which are very dependent on the setup, but I don't think we have general conclusion that if you want a model that is equally good on image and text, what is the amount of image and text tokens in the data that we
Okay, and
Yeah.
if I pair this with the slide of this presentation of the codes, as you call it, in that presentation, basically we see that the text takes much more space.
Yes.
TSNE wise, which means that you have much more data.
For the TSNE.
Yes.
Oh, no, I think because, so let's.
It's a pre-trained, the different pre-trained models.
Let me explain this figure. So here the way we do it is we actually do this analysis on data set of paired modalities. So for example, we have each point of audio is actually associated with one point of text. So it's actually audio captions, same for video and same for images. So because we have like image text data, video text data, audio text data, that's why you have 3 different regions here. But yeah, if you compare only one region to each like modality, I think you get like almost the same size. But again, it's like Disney plot. I wouldn't trust it much.
So they're not the same dimensional, because otherwise text should overlap. Have nothing in common.
Yes. So they are sometimes overlapping, for example, in this case, but it's not always. I think what we should see here is the relative distances of intramodality compared to intermodality, but I wouldn't like look too much on the exact distance here.
Okay, so this is if we stay on this, there is a work called the Platonic representation. I don't know if you know what, that basically point to similar, I would say, and the opposite funding compared to this. Basically, if you scale up data, you will end up with one representation for all. Very simplistic.
I think it's very related to this point actually. So here, because we show that these different representations, multimodal representations, are getting aligned across the model. And if you check the last layer, you see that these modalities are closer compared to the first layer. I think this Platonic hypothesis, which talk about more the convergence of representations of different models, I think it's aligned, not like against what we have here, but I think they like studied slightly different setup. Like they study different pre-trained independent models, while in our case we study like one model, and we try to look inside this one model.
Okay, and in your case, so you're saying that at the end the presentations converge, but you wouldn't want them to be like one of the questions before. Usually you don't want them to like point to the same, like be at the same point, because you will use the complementary information.
Yes, I would say I'm not sure if I want them to be exactly at the same point.
Okay, and when you have, which I understand in this case, so I guess Clip also does something similar. You take the contrasting thing, like you don't take them exactly aligned. So in this case, would it be something that you like? What is your intuition when it comes to multiple modalities or sparse data, medical data, or micro robotic data here? How would the representation should look like?
Oh, I have no idea how they should like, but they should be aligned somehow. To which extent they should be aligned, I think depends on the downstream task. But I expect if you have, for example, like some people, so the definition of different modalities is very loose. It's not very clear, but some people consider maybe like satellite images as different modalities than RGB images. I would say for modalities that are very similar, maybe it's better to keep pushing them to be very, very close in the latent space. But for modalities that are maybe complementary, like if you have video stream and audio stream of this video, I would say it's better to preserve the complementarity of these two modalities than try to like hardly push them the same for the latent space.
Okay. How do you define similar or different?
So the way we do it is based on this simple measure of similarity, cosine similarity. We have different variants, but it's always based on this similarity. You can imagine other similarity metrics, but this is what we study.
Okay, and in state for this one, or it can also be for the ones before. Basically, you have this token aggregation. So I was wondering for this. You have the token aggregation and you control everything from the token. You said at some point that you do with the CLS token, for instance.
Yeah.
How does it pair with this dynamic or / adaptive type of giving many tokens and letting tokens learn whatever they need to learn, like hence complementarity as you mentioned?
So your question, if I have a lot of tokens, how I can selectively choose or skip these tokens?
Yes, that's it.
Okay.
Let me reformulate it. So
Yeah.
what do you think is the best strategy? Is it adaptive? Is it dynamic? Is it you defining? Is it half? Does it scale with modalities?
Yeah.
Is there a rule?
I think that the optimal architecture, at least for what we studied, is this sparse architecture. I think it's better to let the model decide on itself how to route or how to skip different tokens. I think the best way is with the sparse early fusion architectures, where we let just the model figure out how to do with all multiple tokens. So I don't think any hard constraint will lead to the optimal design choice.
And in this case, you have, however, the CLS token, right?
In this case, yes. So yeah, in this case, it's very specific to this kind of architectures because we know that this CLS token is trained to be the summary of all the other tokens. So that's why we just picked it. But you don't have this scenario always.
Okay, and if you had 10 modalities, would you also do a CLS token?
No, I wouldn't do any CLS token. I think if you have the more modalities you have, so I don't think if you have CLS token per modality, maybe it's the easiest to just pick these CLS tokens. But I don't think in recent architectures we still have these CLS tokens. And if you don't have them, I think we need like some learnable modules to do this kind of pooling so that can take all the tokens and put them to very few learnable tokens.
Okay, I understand. Thank you. So for this essentially all the lessons that we learned in your first like 3 chapters, you applied to the last chapter by doing a fishing where you skipped layers and you decided except for the mixture of experts.
Yeah.
So when are the mixture of experts?
So the thing with mixture of expert is it's not the easiest architecture to train in terms of like just implementation and technical details. So because this VLA line of work is quite early compared to the VLNs and LLMs, I think that's why we don't have yet a mixture of experts. But I think at some point it will come. We will have like VLAs with mixture of experts similar to VLMs and LLMs.
Okay, and I was wondering if you have an intuition how all this works. So everything that you have done so far is transformer based.
Exactly.
You take everything, you tokenize it, and then you fit and transformer.
Yeah.
Do you do it before, after, with one layer, one connector, and so on? How would this translate to diffusion? Because VLAs without diffusion.
Yeah, so I would say, so still many diffusions are based on the transformer architectures, or at least many of the components of the transformer, like at least we still have like setback tension, we have residual streams. So even if you have CNNs, I think it's okay. I would say any architecture that has the same generality as a transformer, many of these findings will simply transfer to this architecture. So there's nothing specific, at least to the transformer or LLMs we train on text. It's mainly we have this general architecture, we throw a lot of data, it learns from these data. And I think many of these findings will just fall to any architecture in decent space.
Okay.
You can have it.
Okay, my last question is about future work. So out of all the things that you listed there, there are several that are very interesting and potentially promising. I was wondering for the second one, the data mixers. Would you care like saying more like would it be what data to use? Or do you think that we will end up having something big, massive, but generalist thing that can do several tasks as LLMs are today? Or will you have like specialized, I don't know, agents, embodiments, or whatever you want to call it, that they will be good at their own task, trained with just some data, or data mixers will help in this case? What do you think?
Yeah, I don't think we will move more toward more specialized models at any point soon in the future. I think we'll keep pushing for generalist models. Maybe for some industrial setups, you need to fine tune for some specific use cases, but I think this will adjust limitation of the current techniques that we have now. But at some point in the future, we'll just keep pushing for very generalist models. On the point of data mixtures, what I had in mind is, so it's related to the point just before. What we did is, giving you training mixtures, I can predict the overall performance. But I would like to see more like study on the data mixtures to understand in a systematic way the synergy between different modalities, between tasks. Like for example, some of my work, I noticed that if you train on captioning and VQA, like for example, VQA will transfer to captioning and the other way around. But we still don't know any like science behind this transfer. So we don't actually understand very well the data. And I think this point just to push for more having like science to understand this data more and its impact on the final performance and other aspects of the model.
Okay, but in this case, like follow up to this, both downstream tasks are language dependent.
It could be.
VQA to captioning.
But yeah. For example, like this could be an explanation, but we don't know for sure, right?
Okay, but do you think that for instance, generating audio and generating bounding boxes?
I would say so. So there's other tasks. For example, there's for example visual grounding where you do captioning for localized regions in the image. So I mean, this will easily transfer to captioning because almost it's the same task. Between VQA and captioning, maybe it's because just text output they transfer. But if this is the case, we should see this for all the multimodal tasks, right? Because all these multimodal tasks, especially for these VLMs, are always multimodal input text output, but we don't see this for all the tasks. For example, I saw this only for VQA and captioning.
Thank you.
Yeah, maybe before giving the floor to Mathieu, because this will be the last one. I have really as president, it's difficult to ask questions, but still, so first congratulations for all the work you did and the presentation. But I have a question is more that has been a bit addressed with the questions you got is about what you call about the ethical policies. And but you have I agree for what you said here, but there is also a dimension that you did that is also the multimodality. How do you see that? Because as you see here, and as you said here, you have different roles of this activity. But what you and this is what you have observations here. Do you think that we will observe what is the role of the modalities? Do you see them equal role for all the modalities or not? And how we can deal with that? Because you said we should not put too much constraints on that. But is it the case for this kind of? Because here it's explicit. We put hierarchical and we have high level and low level, so it's explicit.
Yeah, that's a very good point. It seems that this is not very well consistent with having very flexible architectures that try to learn by itself how to decompose itself. I think this kind of architecture is more for the short, medium term. But I think eventually we'll have an architecture that doesn't need this hard separation. One architecture can do very long reasoning and very low level action execution. It's hard to design this architecture because they run at different frequencies. The actions should be at very high frequencies. The reasoning shouldn't be. So designing an architecture with different frequencies is quite challenging. But I think eventually we'll have this architecture. Now, when I say architecture or like flexible architecture, it doesn't need to be like a single rigid transformer model. It can be a very big system, but so flexible that it can allocate different compute to different tasks and capabilities. But yeah, on the point related to multimodality, I think it would play a very big role. We start seeing this multimodal benefits. For example, there's some work, especially from physical intelligence, showing that if you pre-train on multimodal data and action data, you get better generalization. I think many people are pushing in this direction. But yeah, many of the findings, many of the architectural sticks that we have for VLMs, I think they will simply transfer to VLAs and robotics.
Thank you. Thank you for the answer. Maybe I give the floor back to Mathieu.
Yeah.
He said that he will talk a lot.
I will try to not say too many things. I mean, like, I would like to say thanks to the jury. Thank you all of you, Cornelia, Vicky, Mohamed, and Christian, and Graham. Thanks for participating to this jury. Your questions and comments was fantastic and very great. And special thanks, of course, for the reviewers, Graham and Christian, because they have been like As you say, it was very dense, and there is many things in this PhD, and so it's a lot of work. I mean, like to try to summarize to give in a short report. So thanks a lot. I would like also, of course, to congratulate you, Mustafa, I mean, first for your very nice presentation. I think it was not easy because you are already, I mean, like involved in a new story about in this UMass startup and for a couple of months, and so it was not easy and like to prepare and to be well prepared. I think you did it very well. It's fantastic with typically, I mean, like not following exactly the same order as Graham, and so you notice, I mean, like starting with Pekani, for instance. Okay. Just as a context, I would say that how it's possible, I mean, to do a PhD in our world today. I mean, like in the three last years, if we just zoom out a little bit, I mean, of course, but where the world is going, I mean, like it's a first problem. I mean, like to be able to be focused on PhD and not be affected in many different ways, but of course you are I mean, you are coming from Lebanon, and so at least for sure, it's the geopolitics has a big impact. I mean, from your family and to stay. I mean, like so. I mean, like so nice, so positive, and so great in your work. I mean, like and so open mind. I mean, all the time you were here, it's really fantastic, and I have to say that first. The second thing is that I have to say also that the science was so crazy. I mean, like that for these 3 years. And we can say that you born, I mean, at least your PhD exactly at the same time as ChatGPT. And so it's a kind of AI crazy revolution. And like the second one for us, I mean, like, because we had our vision one, I mean, like 15 years ago. But I mean, like, and so with a subject like vision and language, what we can do, I mean, like when this kind of crazy LLMs are coming, and so you need, and you did very agile, I mean, to be able to be flexible, I mean, like to really adapt, I would say weeks after weeks, and not even months after months, I mean, like how to reconsider the problem, how to redefine, I mean, our objective, our goals, and I think just to see the number of things that you did, that you were very successful to do that, and it's fantastic. And just to finish, I mean, I would say, I mean, like sometimes I try to resume, I mean, like what I think to my PhD student as one word. So, do you have any idea of how I can summarize you as in one word? No? No idea? No idea. I would say, I think you have perhaps this word more or less one slide on two. I mean, like it's scaling. You are the scaling guy. I mean, for me, you are the scaling guy. And it's a very positive. When I say that, I think it's not always the time. I mean, you really changed my way of thinking about experiment during your PhD by pushing, I mean, like generalization as a kind of boring term, and to change this generalization for scaling. I think, or let's say differently, I think now when we are thinking to experiment and to validate something in the team, we are not just trying to be so down a few data sets as usual, but we really try to see if whatever the kind of method we propose, we are able to scale, and how this method is able to scale. Okay, and so thank you very much for that, and I hope you will be able to scale all the orbit humor. Thank you very much.
No, thanks, Adi.
So now we finish the time of trade. We stay here.
Yeah, we stay here.
So we stay here. We need how to close the retreat.
Yes.
Okay.
How you doing?
Let me try.
Doing that. And then we stay here. So Christian and Graham, we just stay here and
C'est comment? Non, c'est comment? Non.
Je sais pas.
Je vais regarder, mon chapelet. Ouais, c'est fini, on va couper le flux. T'arrives? Ok, super. Ah, mais là, je suis dehors, je suis dehors. Je suis bien. Il arrive. Ouais. Bon, on verra ici. Il va 23 minutes qui coupe le.
Bien sûr, bien sûr. Bien sûr, il faut.
Oui, bonjour, ça va la suite, elle va parler, vous m'avez appelé tout à l'heure. Oui, mais j'avais laissé ce numéro.
Tu peux juste bien remettre en vie, tu coupes juste le flux et tu.
Ouais, je coupe juste le nom. Ouais, merde, ça c'est pas ça.